If you can hear my voice, please type Y. If you can hear, yeah, okay. Then we'll start. There are 5 people, that's okay, fine. Because it's 9, so too late, okay. So we were talking about LP analysis the last time. And what did we get from LP analysis? We found that LP analysis or linear prediction analysis, finally we get an error signal which represents, in a noisy pattern, it represents the glottal excitation signal or source excitation signal. And we get the transfer function of the system, from where we can detect formants or vocal tract resonances. And then even we could find out, using the Levinson-Durbin's algorithm, the relation between consecutive areas of the tube that we model in source filter theory, consecutive cross-sectional radius. So this is what we found. So basically, but the two biggest achievements were we were able to indirectly find out the vocal tract system and the excitation source. There is another very popular technique particularly devoted to this problem, means how to find out, segregate, because finally the speech signal is a convolution of an excitation signal and a system, which system has different parts, of course, glottal model and vocal tract and lip radiation, all that, but you can consider all this is a system, a complete system, and it is convolved with that. And the system is mainly influenced, as we have seen. This is the main part which influences the system, or whose characteristics are present in the system, so to say. So, how to now, speech is the waveform that we have available, that is what we record, that is in our hand. How to separate this, get this information from the speech signal? That is, this process is called deconvolution. How to separate out the components of separate the source and filter, or separate, or instead extract the source and filter information from the speech signal. So LP analysis, we have seen it does a very good job. No technique is perfect. We have seen that this is quite noisy, and there are other issues with the vocal tract system. We have seen if we change the order of the LP analysis, the P value that we saw, that is which is related to the number of poles in the transfer function, then we can get, depending on the value of P, very some inaccurate or spurious analysis we can get. So there is another technique, hence, that people use. It's called, in speech processing, it's called homomorphic analysis, or more popularly known as Cepstrum analysis or Cepstrum. So what happens is, what happens is we have our speech signal. Now it is convolved, and what is convolution? It is just contains multiplication, summation, then time shifting. All these three results in the output called convolution, and that's why once you convolve two signals to result in an output, the original signal, to get it back, it's not so easy. However, if suppose we had something like, if there was somehow some operation, let's say D star, I will denote it by D star, some operation we could do, where we could convert this into a summation, then things become much more easier, much more easier to separate, segregate, and analyze. This operation is called homomorphic analysis. This is an operator. To have an operator, we use an operator, we denote it by D star or whatever you already know. If we apply it on a convolved signal, then we can get in a summation form the operated versions of the individual signals. So this is called homomorphic analysis. So in speech, now let's see what happens in speech. So here we have S of n equal to En h of n. So S of e to the power j omega equal to E of e to the power j omega and h of e to the power j omega. So in the frequency domain, it is multiplication, which is a bit better than convolution, let's say. Now, if you take log of this, log E, when I mean log of E, then what will happen? This will become a summation. So this log of E, you can say it is like in homomorphic analysis, we are saying we need to use an operator which can convert it into a summation. So it's like this log of E becomes that homomorphic operator in the case of our speech. If you go to the frequency domain, it behaves like that. So if somehow now let's see what happens if we do this. So first of all, this is your S, okay? Remember, this is your S e to the power j omega. Here it is mentioned as X, okay? So you get this S cap n. So what is happening here is, so we have S of, I will take on the slide. We have S of n, which gives S e to the power j omega. So if you take inverse Fourier transform, you will get S of n. If you take Fourier transform, it will S e to the power j omega. But what will happen if you take the log of this? Then what will happen? If you take the log of this Fourier transform and then do inverse Fourier transform, what is the relation? We denote that by S hat n. So basically S hat n into 1 by 2 pi So now we have to analyze. Now we have to analyze. See, because log e to the power j omega, we know that what we can say that log it contains e to the power e j omega part plus so there is one part. So you can say this Sn is something like E cap n plus H cap n. It is a combination. You can say this, it is a combination of two components, two additive components are there. One which is related to the system and one which is related to the source. One which is related to the source excitation, one which is related to the system. So this is the part, as you see, which will be related to the source, and this is the part which will be related to the system. So this now, so if you get S hat n from log of S to the power j omega, it's basically E hat n plus H hat n this whatever you get now, this n generally if it was S of n S to the power j omega, so what we this n we called as time index. But in the case, once we take the log of the spectrum and then do inverse Fourier transform, whatever we get, we call n as Q frenzy. So this is just an interplay of frequency. So when they came up with Cepstrum analysis, then notice that this is very related to, we are just simply taking log, we are not doing something absolutely something miraculous here. So some of the terms, they just simply shifted the words and came up with. Similarly, the word Cepstrum. This is known as Cepstrum. This is a term. This is spectrum. I think this is Q frenzy. Yeah. You just check it. So this is from spectrum. They just rearrange the words and came up with Cepstrum. This is S hat n. So now what happens is an interesting phenomenon occurs. So you have this S hat n S to the power j omega log of. So you will get n, which is Q frenzy. Some values you will get. Nobody knows whatever values you get. And this is your simply log spectrum. This is not even log magnitude. I am taking I am not taking a magnitude. This is also known as hence complex Cepstrum. This is also called complex Cepstrum. If you take the log, then maybe we will discuss a little bit about that. It is called simply called Cepstrum. Okay, but this is complex Cepstrum. So here, suppose, so you have these values. Now you can choose. So whatever the log comes, obviously this is a imaginary number. So basically, you are taking log on for both the real and the imaginary part. Okay, this you can in fact log e s e to the power j omega. Let's say it is, you can write it as e to the power j omega is angle of magnitude, and e to the power j, you know this how to do. So if you take log of this, what will you get? First you will get this magnitude part, log e s e to the power j omega plus j angle of s e to the power j omega. So imaginary number you will get. Here is your real part, here is your imaginary part. But so it's an imaginary number, so we cannot plot it here. You need you can plot it if you want. If you take a polar plot, then for every value of omega you will get some value. That's how you can plot it. That is one way to plot it. Otherwise you will need omega on one axis, and it will be a three-dimensional plot otherwise. So in polar form you can use a polar plot, but anyhow does not that's not very important. So you have this and you will get an imaginary number for a complex Cepstrum. Now you can do something called liftering on this Cepstrum. This is a complex Cepstrum. Remember, this is the complex Cepstrum. Liftering. What is liftering? It is filtering rearranged. This word is filtering rearranged. Okay. So what is liftering? It is simply you get your complex Cepstrum, some values you get, you put a window. Basically, you select some and put the rest of the zeros. You select some of the components and put the rest of the thing zeros. This is most probably called low time liftering, because you have selected only the first few components of this Q frenzy. On the other hand, you can put another window, something like this, only pick the high, this higher indices. So you will get, these are all zeros, something like this. Low time liftering, high time liftering, something. So now from this, what we find that we have found that this component, these first few components of this Cepstrum, it represents your slowly varying this system, because system is slowly varying compared to we have seen if you take the Fourier spectrum, we have seen a magnitude spectrum. The system represents the envelope of the speech signal, and the excitation generally, let's say if in a voice speech, it represents these small peaks that occur at f0 to f0, this the fundamental periods. So what is found is, if you take the first few components by low time liftering and then you do this inverse Fourier transform, then what you will get this log e, an estimate of the envelope basically. These first few components, it's found empirically by trial and error that if you take these first few components around 10 to 15, somewhere in that range, 10 to 15 this number, then you will find this log spectrum, you will get something like this. On the other hand, if you take this high time lifted components and then take inverse Fourier transform, you will get an estimate of log e to the power j omega. And you will find that they are we saw previously how the Fourier transform of this train of impulses or random noise looks. But that's what you will get. This is particularly important. And there are methods devised based on this low time lifted Cepstrum and high time lifted Cepstrum to find out the formants, determine the formants of vocal resonances and the period, speech period of the speech signal, speech period or fundamental period of the speech signal. But this is, in a nutshell, what today's class is about. So let's go back. So what we were doing, what we are doing, just imagine this is S instead of X, S. So this is the complex Cepstrum. This is the complex Cepstrum. Instead, we could also take only the magnitude. This is called the Cepstrum. In fact, this Cepstrum that we take only the magnitude, which means S e to the power j omega. We know S e to the power j omega is this e to the power j omega and multiplied with h e to the power j omega. So if you take log, it will be simply summation. This will be a real number. There is no this value. It has no complex. This one. This will be a real number. Here it will be a complex number. This will be a real number, and then you take inverse Fourier transform to get this Cepstrum. If you take the complex entire complex spectrum, Fourier, this entire spectrum, not just the log magnitude, then you will get your complex Cepstrum. So this is what we get. We just talked about it. So we have talked about this homomorphic analysis. What does this mean? Means if you have something convolved, in our case the speech signal is x1 is our let's say en and hn, and this is our speech asset. Then we want an operator which will somehow separate the two components. So what we do, this Sn in our case, we'll get our discrete time Fourier transform. We take the log, and then you take from the log, this from the spectrum, we'll take inverse Fourier transform, and then you will get your Cepstrum, complex Cepstrum. If you take magnitude only, then it will be only the Cepstrum. Now, from x hat n or s hat n, x hat n or s hat n, whatever, you do some kind of liftering to get y hat n. Some liftering you get, select only a few components. Then what you do? If you do discrete time Fourier transform, this is what you go. This is the log. It's like the we imagine the effect of the log to be there. That's why to get, because it is log is there, effect of log is there, we do e to the power, this e to the power of whatever we get, so that we get the Cepstrum for the low time or high time lifted signal. And finally you do IDFT to get y. So, but this part is generally we are not concerned with that. This is till this part. we are more constant. So this yn, as I said, there is a window. Gn is a window, a lifter, just a play of words with filter. We put a window there, a rectangular window, basically selecting the first few components or the last few components of the Cepstrum, and then we do this discrete time Fourier transform to get this. Oh, one thing I forgot. Maybe yes. So here I was saying inverse Fourier. Of course not. This is not inverse Fourier transform. This is Fourier transform. After you do liftering, obviously you do Fourier transform to get this log influence spectrum. It is not inverse Fourier transform. Sorry, because what is this is Fourier transform in this direction, and inverse Fourier transform in this direction. That's how you get the acidity power j omega. So obviously, if you have a component, so you will do Fourier transform to get this. This homomorphic or lifted signal spectrum. So what else? Yes, these are all play of words. Q frenzy, liftering. This is from filtering. Q frenzy is from frequency. Cepstrum is from spectrum. So just play of words. Yes. So now, how do we implement it? Again, short time analysis of speech. We'll take a chunk, a frame of the signal, a windowed frame of the signal. A window is centered around n, a value n or n hat, it is mentioned. So if your signal is something, this is your m, let's say your window is, some window is there, whatever, it could be dome shaped or rectangular, whatever suits the purpose. And then here Cepstrum, as I said, here they are using Cepstrum instead of complex Cepstrum. So log of magnitude of the signal. So this x here basically represents the speech waveform. Yes, and had it about j omega this is what it represents, and then you do whatever is you do this inverse Fourier transform to get your short time Cepstrum. Yeah, so now let's have a look at what I was saying. So this is a voiced frame. For a voiced frame, it's a 40 millisecond, no, this is, oh, the duration they have not mentioned, does not matter. So this is a voiced frame, whatever duration they have taken. So this is your log STFT. So if your voice frame was there is a voice frame, or let's say centered around n, there is a frame, voice frame you have taken, you took the STFT, log STFT. For that frame centered at n. So if you took that log magnitude of that, this is what you will get. Okay, the red color, whatever you are seeing. The blue color ones is the actual log STFT. Okay, the blue color one is the actual log of this term. What they have done in the red color is they have done low time liftering. So whatever Cepstrum they were getting, they took only some, here I think, whatever they took, I think 8 or 9 components, something like that. They took the first 8 or 9 components And then they did Fourier transform and they got this red color. You can see it tracks the envelope of the signal. Now on the this is for voice. For unvoiced, again they have done the same process. In unvoiced, of course, yeah, again, so you can see what happens here. These are the, you can see identified. There are probably 4 resonators here in voice. Similarly, in unvoiced, and these resonators are what? In voice pitch, you know, the higher resonances are weaker. In unvoiced, again, they have done low time liftering, and then when they took the Fourier transform, you get the log magnitude spectrum. You can see these areas are probably the formants, and you see as frequency increases, the formants become stronger in case of unvoiced speech. So I wanted to go for MFCCs, male frequencies today, but seems like there will be no time. Means a perceptual part of speech analysis, a speech perception, how speech perception happens, but I think there is not much time left. So we'll just recap what we have studied. So we have this speech, which is a convolution of the source excitation and the system. Our goal is to extract information from the speech signal about these two things. Extract information about the source and the filter, which are convolved in accordance with the source filter theory. Source filter theory says that these source and filter signals, they are convolved. So it's difficult to extract information about them easily. If it was a summation, then it would have been far easier. But because it is convolved, it is quite difficult. So our aim is to do deconvolution. So in this perspectives, homomorphic analysis becomes useful. Homomorphic analysis uses an operator on a convolved output. And what does the operator? It operates separately on the or it breaks up the convolved output into separate components. So in the case of Cepstrum or complex Cepstrum, what we do in the case of Cepstrum or complex Cepstrum, we use this homomorphic analysis in the frequency domain. So what we have is S of n, S to the power j omega. If we take log, that means we know S of e to the power j omega is e to the power j omega according to source filter theory, and h to the power j omega is a multiplicative. So if you take log in the frequency domain, then we get it in additive terms. Log of e this one plus log of H. So now if you take inverse Fourier transform of this signal, we get S hat n, and you know from the properties of Fourier, so that if x1 n has some x1 e to the power j, x2 n it has x2 something, and if this is sum, this will also be sum. This is a basic property of Fourier transform. So we can expect that we'll get something related to these terms. We will get En plus Hn. So this is the basic concept of Cepstrum. So most of the time in speech, this is the complex Cepstrum. Most of the time in speech, we'll use the log magnitude part only. You have a Sn. So S e to the power j omega. So we'll take the magnitude part and log of that, and then we get we represent it by C of n. You can write even S of n, does not matter. S at n, whatever. Let's put S at n. Very easier for me. So it's just a representation. So you get this. So again, the magnitudes, as you know, it becomes separated into two parts. Complex Cepstrum, the Fourier transform after you take means the log Fourier spectrum is a complex number. Here it will be a real number. This will be a real number. And again, the same thing. We expect that this will be related to log of magnitude of e to the power j omega plus log of magnitude of h, this part. So you have got this S hat n. Now we have found that this n is called Q frenzy. Instead of time, we call it Q frenzy, play of terms, play of words. So we have this n. If you take the first few components, whatever comes, first few components, this is called liftering. You put a window basically, indirectly we say you put a window. Okay, so let's say y hat n equal to some window g of n or w of n into s hat n. You take a window. This is called liftering. So you are left with only this part and rest are zeros. And then obviously you do Fourier transform. Whatever Fourier transform is a log magnitude something you expect, or we find that this represents the envelope of the speech spectrum. Indirectly, it represents the vocal tract, the system. We say H hat it is because we don't know exactly how to separate out. Those are, this is S hat n equal to E of n plus H of n. We don't exactly know how to separate, but we found empirically that if we take the first few components, then whatever, if we do Fourier transform, we get a spectrum, log spectrum, which tracks the spectral envelope, and hence we can say, even though this is not H hat means not exactly the system, not exactly, but it's an estimate of the system Fourier, log spectrum, log magnitude spectrum of the filter. So this is basically what we discussed today. This is Cepstrum. This is also a very important, simple but important tool for analysis. We have seen this figure. What happens? So if you take this is your voice. If you take a segment frame of the speech signal, you can see the blue lines here. The blue color is a log spectrum, log magnitude spectrum, log of magnitude of s to the power j omega. That is the blue lines. But if you see the red one, this is taking the first few components of the Cepstrum and then doing Fourier transform. It tracks the envelope and it helps you determine the formants. So same thing you can see for unvoiced speech. So that's all for today. There is nothing more to discuss in today's lecture. Next lecture we'll discuss about the perception of speech, something called as Mel frequency Mel frequency Cepstrum coefficients, or MFCCs, a Mel filter bank. So please give your attendances and please leave the lecture.